Hello, Science 30s. Today we're going to be talking about Hess's law, which is also the theoretical heat of combustion. So the question is, how much energy does a candle have? How much energy does ethanol have? And how would we determine that? How would we determine the potential energy of those two substances? And one way we can look at it is if we burn those things. If we burn those things and measured the amount of heat coming off of those when we burn them, then we would be able to determine how much energy they contained. One way we can do that is by using calorimetry. Now, you might have used calorimetry in some previous science classes, even in junior high, some teachers cover this. Very simply, one setup very simply is this one here. And what we see here is we see a very enthralled student watching the thermometer here as this candle is being burned. And there's about 20 milliliters of water in there, and the heat from the burning of this candle is heating up this water, which will obviously lead to an increase in the temperature. Now, one thing you're going to do before this experiment is you're going to get the mass of the candle before and the mass of the candle after, and then you can determine the amount of energy that is in paraffin wax, for example. Paraffin wax is uh, a determined chemical formula. So then what we can do is we can use mass and molar mass to come up with the number of moles that were actually burned of the paraffin wax, and use the temperature difference here to then determine the amount of energy. We can also do that with like an alcohol burner. So a little alcohol burner, we could figure out the energy per mole that's contained in ethanol. We could do it for a peanut. So I've done that in classes before where we take, usually it's a little bit more robust than this, a setup. We usually do it in a pop can, which is insulated so that we're trying to contain as much energy as possible. But you're burning a peanut, you start it on fire, and you get the mass of the peanut before, the mass of the peanut after, however much burnt, and then you look at the difference in the temperature of the water in the pop can. And that way you can determine how much energy is in food and things like that. That is literally how they used to determine the amount of energy in food, is they would use a bomb calorimeter, which is a much more scientific instrument than we would have used in class, but it's well insulated. You have a container in here which burns the reactants, okay, and then the water surrounding it gets heated up, and no energy is lost in this system. The energy is just transferred from the burning here into heating the water. Here, a lot of energy is lost, obviously. Like some of this heat is going to go out like this and go out like this. It's not 100% going to go into that water. And so then now what we're going to do today, though, guys, is we're going to look at a theoretical way of doing this. How can we do this, and how do scientists do this now? They don't use Baum calorimeters. I mean, they would, but I mean, in general now, guys, they're using Hess's law to determine the amount of energy in food. And so, I mean, in a way, guys, when we break down food in our body, it kind of is like just a slow combustion reaction. Okay, it's being broken down. Some heat is created, not enough for it to start on fire. But what we do see is that we start off with some reactants, okay, and you can see the chemical potential energy of that is quite high. So in this case, it's octane. So this octane is just waiting for something to happen. Then it starts to happen. It starts to burn. As it starts to burn, its chemical potential energy decreases. There's not much you can do with carbon dioxide and water. These do not contain very much energy compared to something like octane, which will burn if you put it in oxygen and fire. So now the chemical potential energy has decreased significantly in these from the reactants to the products. But we see that the kinetic energy has done the opposite and equal. Okay, so while it started off as very low, the kinetic energy here not very high, but as it started to burn, it started to get hotter. Things started to move quicker, and then we see the kinetic energy is much higher on this side. And so again, that of course has to do with the first law of thermodynamics, that energy cannot be created or destroyed, but only transferred from one form to another. And so in all combustion reactions, we're looking at the chemical potential energy decreasing and the kinetic potential energy, or sorry, the kinetic energy increasing by the same amount. So in Science 30, what we're going to be doing is we're going to be looking at, we have a couple tables and formulas that we're going to be looking at. And this table is in your data booklet, and it is, these are going to be the standard heats of formation of selected compounds at 25 degrees Celsius. And these are the numbers we're going to be using right here in this class for this formula. The formula that we're actually going to be using is going to be right here. And it's on the same page of your data booklet. And there's the formula. Whoops, change my thing there. And there's the formula right there. And so what we see here is we have the delta underscore subscript R and then capital H. And that is going to be the energy change of the entire reaction. And how do we determine that? Well, we first of all then figure out the sum. That's what this Greek letter sigma means right there. The sum. N means the number of moles that reacted. And then this delta F H degree symbol, which is the standard molar enthalpy of formation. And then that's of the products. And then we're going to subtract the same thing, the sum of the moles times by the heat of formation of the reactants. And once we subtract those two, we will then get the energy change, and we should be able to determine and predict now whether any chemical reaction is going to be exothermic or endothermic. Okay, so let's get into a practice example here, and we'll see how this works out in reality. So again, guys, what we're doing here is we're predicting. It's almost like a prediction. This is not basically what we're doing, guys. Is we're saying, okay, how much energy does methane have in this question? So the balanced chemical reaction for the combustion of methane is as follows. So we have methane plus 2 moles of oxygen reacts to create 1 mole of carbon dioxide and 2 moles of water vapor. And of course, what we could do, guys, is we could start the methane on fire, and we could measure the temperature difference, get the mass of methane before, get the mass of methane after. But what we're going to do instead is we're going to use the standard heats of formation. And what we're going to do is use that formula to then predict how much energy will be released when we burn so many moles of methane. Okay, so in every single one of these questions, we're going to be making a table just like this one here. Just practice drawing this, guys, a couple times on your own just before you even get into questions, okay? It's a pretty easy table to draw. I mean, I just drew the big, huge outline first, okay? Put my substance, the coefficient, and then the heat of formation down here. And then we have our products. Our products go first. That's very important to realize here. Products go first over here, and then reactants over on this side. There's usually 2 products, 2 reactants. If there happen to be 3, then you would have to split this up into 3. You might have to split this up into 3. But in general, there'll only be 2. Remember, guys, Science 30, I will always give you a balanced chemical reaction. So I will not say, hey, what's the standard, or what's the energy change for combustion of methane. I would give you this formula, this chemical formula every time. Okay. All right. So let's start filling this in. So now we see our substances of our products are going to be carbon dioxide. State of matter is really important, so make sure you put that. Okay. Our other product is going to be water vapor, not liquid water. You don't get a liquid puddle of water underneath a fire. Our reactants are going to be methane gas and oxygen gas, just like that. The coefficients in front of the carbon dioxide is going to be a 1. The coefficient in front of the water is right up here, and there's our coefficient, which is the 2. Coefficient in front of the methane is going to be a 1, and the coefficient in front of the oxygen is going to be a 2. And so we do that there. Now, we need to go to our other table and find out our heat of formation of all of these things. So let's get out let's go over here. First of all, we're going to look up carbon dioxide gas. Carbon dioxide gas is right over here. Let's find it. Carbon dioxide right there. And the standard heat of formation of carbon dioxide gas is right there, negative 393.5. So let's go back to here, and we're going to write that in here. This is negative 393.5. And this is all in kilojoules per mole. Just so because I don't have room to put that in there. Standard heat of formation of water vapor. Again, be very careful when you're doing this, guys. I'm not going to go back to this table again. You guys can look it up on your own, but I'll do it this time again because here we have two waters listed. One which is liquid, one which is gas. And obviously in combustion reactions, we want the gas one right there, the vapor. And that will obviously change your answer if you use the wrong one. Okay, so in this case, we're using negative 241.8. So let's go back here and put negative 241.8. I'll trust that you can look up methane on your own. Methane is negative 74.6. Okay, now we're at oxygen. We're at our last one, which is a little bit of a special case. We go back over here, and where's oxygen? It's not on there. Okay, so what does that mean? Well, notes. Elements are given a value of 0. And oxygen is an element. It is not a compound on its own. And so it is an element. And so the standard heat of formation of that element would be 0. So I just added in the formula now that we're going to be using. So this is going to be the energy change of the reaction, which is right here. In this case, it's also going to be equal to the theoretical heat of combustion, we call it. So whether you put the R there or the C doesn't really matter at this point. Okay, and that is going to equal the sum of the number of moles multiplied by your heat of formation of your products, and you're subtracting the sum of the moles multiplied by the standard heat of formation of your reactants. So this is going to be quite a big formula, but that's why we use this table. This table helps us organize our mathematical formula down below here. Okay, so we're going to I'm probably going to run out of room here on the thing. So what I'm going to do to try and be organized, I'm going to use big square bracket here. So my two products are carbon dioxide gas and water vapor. And so what we're going to be doing here is we're going to say 1 mole multiplied by the standard heat of formation of, so again, what we're doing here is carbon dioxide. So it's 1 mole of carbon dioxide multiplied by negative 393.5. And I'm going to use units here, kilojoules per mole. And there's a sum. So the sum means we need to add these two products together. So we're going to add to that. What else? We're going to add our water vapor. So there's 2 moles of water vapor multiplied by the standard heat of formation of that, which is negative 241.8 kilojoules per mole. Okay, so I can end that little bracket or that parentheses, and then I can put my big square bracket there because I'm done with that's my sum of my products. Now what I'm going to do is I'm going to subtract, and I'm just going to go on my second line here, my reactants. And my reactants, the only one that really counts is going to be the methane, which we have 1 mole of. And then we have the standard heat of formation there of negative 74.6 kilojoules per mole. And I'm going to toss it in this time, but it doesn't really matter. You don't even need to include this in a way. But we're also going to have 2 moles of oxygen gas, which has a standard heat of formation of 0. And there we are. That's my entire mathematical relationship. Okay. And I don't usually show the next step. I just usually, because I mean, you're doing this now all in your calculators. Okay, but if you enter this into your calculators, you will get a final answer of negative 802.5. Now notice here, moles cancels out with moles, moles cancels out with moles, moles cancels out with moles, and of course this one just cancels out completely. Okay, and uh, and then this final answer then would be in kilojoules. And there we are. That is the energy change that happens in when we burn methane. We should look at the symbol or the sign in front of this. So we notice that this is negative 802.5 kilojoules. The negative refers to the fact here that our methane, well, the reactants have more potential energy than the products, which means energy was released during this reaction. That means that this would be an exothermic reaction. If this is ever a positive number, then that would mean that this would be an endothermic reaction and actually uses energy from the environment around instead of releasing energy. And and yeah, so that's what you need to know about Hess's law. Once again, try to practice drawing that a couple times, please, and try and do the couple questions that I assign, and you should be good on this. Have a good week, guys. Thank you.